Okay, so today I'm going to go over how to solve improper integrals with vertical asymptotes. Now, this is the third and hopefully final video I've done featuring improper integrals. The last two have been over improper integrals with bounds of infinity. This time, however, it's going to be a video over improper integrals in which the integrand is undefined at some point on its interval. Now, recall that an improper integral is an integral that just can't be solved in its current state. It has to be solved ideally with a limit. And so that's what we're going to do today. Okay, so at the top of this page, if you ignore this condition over here, I'm giving you the process of which you should employ if you wish to solve an improper integral. More specifically, if you include this condition, the process of which you should employ to solve an improper integral featuring a vertical asymptote. Now, this vertical asymptote occurs at point B. That's because f or g of b is equal to 0 at this point, and therefore it's undefined. So what I'm going to do quickly is I'm going to give you just a generic curve with a vertical asymptote. Let's say there's a vertical asymptote that exists at x equals b. Let's say there's a point over here, x equals a, as well as one over here, which we'll call x equals c. So as I said, there exists a vertical asymptote at x equals b. So I'll draw, to my best ability, a curve that models that. Okay, good enough. And this curve, we'll say, can be modeled as f of x over g of x. So if you wish to find the integral from a to c, you could literally interpret this as the area underneath the curve. The issue exists, or there exists an issue in which x equals b doesn't have a value, and so you can't find the true value underneath the curve because there exists no true value. So in order to counter this, we can take the integral from a to b, or from a to c, and split it into two separate integrals, the integral from a to b, as well as the integral from b to c. And that's essentially what we're doing up here. We're splitting the integral into two separate pieces. However, x equals b is still undefined, so you can't really find the area underneath the curve from a to b or from b to c because b doesn't have a value. And so what we do instead is we take the integral from a to a point infinitely close to b, or interpret it as a value infinitesimally lower than b, such that it's almost b. For all practical reasons, it's b, but it has a value, and so it can't truly be b. And so therefore you can find the area underneath the curve. And so we do that for a to b, modeled over here. We take the limit as n approaches b of, well, this over here should be a, I suppose. The limit as n approaches b from the left of the integral from c to n f of x g of x. Now in this instance, c is going to be a, and over here, a is going to be c. So that's essentially what we're doing on both separate sides. We're splitting it into two separate integrals, and we're taking the limit as from one point to the asymptote, or to a point infinitely close to the asymptote, and we're combining that with another integral infinitely close to the asymptote to your other bound. And so that's how you solve a vertical asymptote. An improper integral featuring a vertical asymptote. Okay, so this is practice problem 1 of 2. We're told to find the integral from 0 to 3 of natural log x with respect to x. And at first glance, this problem seems very straightforward. The only difficult thing being that we have to find the integral of natural log x. However, it's not so straightforward because there exists a point on this interval, as in x equals 0 to x equals 3, at which natural log x is undefined. That point being 0, because natural log 0 does not exist. There exists no. It's simply undefined, and so we can't really solve this in its current state. So we're going to have to employ some sort of limit. What we're going to do is we're going to equate this to the limit as, let's say, n approaches 0 from the right of n to 3 natural log x dx. Now we take 0 from the right because we can model that as 0.00 ... 0.1. It's infinitely larger. It's infinitesimally larger than 0. And so that is the point at which we're trying to find it, essentially. Now, we can't take the limit as n approaches 0 from the left, because that would result in x being a negative value. It would be a point infinitesimally smaller than 0, which ends up being slightly negative. And since we can't have the natural log of a negative number, you have to take the natural log of a positive number. So we're taking it as 0 is slightly larger, or sorry, as n is slightly larger than 0. So that's what we're doing in this instance. From here on out, we just need to solve our integral, which I'll do down here. In fact, I'll do it in another color because yellow is getting boring. So the limit as n, let's just forget about the limit for the time being, because we just want to integrate this. So the integral from n to 3 of natural log x dx. Now, natural log x can be modeled, or we can solve this using partial integration. We can assign natural log x to u. Therefore, du is equal to 1 over x dx. And we can assign 1, the constant of which natural log x is being multiplied by, as dv. And therefore, v is equal to x. So from here, we can just use the formula uv minus v du in order to solve this. And so we can say that the integral from n to 3 of natural log x dx is equal to uv, therefore x natural log x, minus v du, that being x times 1 over x dx. And we, of course, have to take this from n to 3. And so we can simplify this a bit by saying we have x natural log x. Now this over here, the integrand is equal to 1, and the integral of 1 is x. So we end up with x natural log x minus x from n to 3. And so I'm going to write that back up here near the bulk of our equation. So we can say that this is equal to the limit as n approaches 0 from the right of x natural log x minus x from n to 3. And so from here, we can simply solve. Give me a moment because I want to just clear up some of the problems, or sorry, some of the mess down here. So just give me a moment. Okay, so I apologize because I accidentally exited out of the page. So the formatting may look a bit different, and I cleaned up this mess at the bottom. But anyways, we're going to finally solve our limit over here. So we're going to equate this to the limit as n approaches 0 from the right of 3 natural log 3, because we can finally begin filling in our bounds. 3 natural log 3 minus 3 minus n natural log n minus n. And I'm going to actually distribute this negative sign over here such that we actually end up adding n. So I'm going to do that, and I just did that. And from here, we're going to partially take the limit as n approaches 0 from the right. You'll see what I mean. We're just going to simplify this for a bit. So we're going to say that what we have currently is equal to 3 natural log 3 minus 3. We're going to take the limit as n approaches 0 from the right of n over here. Now, n is so little larger than 0 that it is practically 0. And so when we say that we're taking the limit as n approaches 0 from the right of n, we can really say that we're really just adding 0 in this instance. And that's exactly what we're going to do. Now, I'm not going to put this in my final equation because it's 0. We're just adding 0. It isn't really worth it. And then finally, we're taking the limit as n approaches 0 from the right of n natural log n. Now, this is actually indeterminate. Try to recall what a natural log x graph looks like. It looks something like this. Oh, that's terrible. Something like this. Now, as we come closer to 0, our value becomes closer and closer to negative infinity. So when we're taking the limit as n approaches 0 from the right of natural log n, we're really equating that, we're really solving for negative infinity. That's really equal to negative infinity. So over here, I'm going to write that the limit from 0 from the right of natural log n is equal to negative infinity. Now, this itself doesn't make a term indeterminate. However, if we were to divide this over here, or if we were to to model this as natural log n over 1 over n, well, of course, this is equal to n natural log n, but you may notice that the limit as n approaches 0 from the right of 1 over n is equal to infinity. So as you can see, since we have a function modeled as, or a limit that is equal to negative infinity over infinity, and therefore an indeterminate form, we can take L'Hopital's rule. And so we're going to do that. We're going to rewrite this term over here as natural log n 1 over n. And bear with me because I'm not going to write out the full proof for L'Hopital's rule because this isn't an AP test, so I'm not going to. But I am going to say that the limit as n approaches 0 from the right of of natural log n 1 over n is equal to 1 over n negative 1 over n squared. Therefore, I think this is equal to negative n. So we can say that this over here is equal to 3 natural log 3 minus 3 minus the limit as n approaches 0 from the right of negative n. And therefore, our final integral from 0 to 3 of natural log x with respect to x is equal to 3 natural log 3 minus 3, as this over here is basically just equal to 0. And so that's our true value of our integral from 0 to 3 of natural log x dx using vertical asymptotes. Okay, so this is practice problem 2, and also our last practice problem at that. We're given the integral from negative 1 to 1 of 1 over x squared dx, and we're trying to solve it. Now, hopefully you should immediately recognize that this is going to have to be an improper integral because there exists a point at which our integrand is undefined on this interval. That point being x equals 0. Because if we were to plug in 0 for x, we'd end up with 1 over 0, and that's obviously undefined. So we're going to have to split this into 2 separate integrals. And I should add that we're taking the limit as some variable approaches 0, or a value infinitely close to 0. So we're going to assign this to the limit as n approaches 0 from the left of the integral from negative 1 to n 1 over x squared dx plus the limit as, we'll say m, since we've already assigned a value to n, approaches 0 from the right of m 1 over x squared dx. Now, if we were to ignore c, the integral of, or the antiderivative of 1 over x squared is negative 1 over x. So we're going to assign what we currently have to the limit as m approaches 0 from the left of negative 1 over x from negative 1, sorry, that's wrong. Sorry. No, wait, that is right. From negative 1 to n plus the limit as m approaches 0 from the right of negative 1 over x from m to 1. So from here, we can start plugging in our values. We can once again assign this. Actually, let me choose a different color. Purple is boring. We can assign this to the limit as n approaches 0 from the left. Now, I'm not going to keep these boundaries as we don't really need them at this point, of negative 1 over n minus 1. Now, this is negative, I should add, because if we were to subtract or this term over here, we would, of course, turn it positive, seeing as it's negative. But once we plug in negative 1, it is once again negative. So that's why we're subtracting 1. Minus 1 over minus 1, seeing as we plug in 1 for x over here, plus the limit as m approaches 0 from the right of 1 over m. Okay, so from here we can continue solving for our values. This over here is essentially equal to infinity. Now I'll give a reason as to why. If we were to take the limit as m approaches 0 from the left of negative 1 over n, we'd essentially end up with 0, because 1 over any value infinitely close to 0, we'll say 0 minus in this instance, is going to be equal to infinity or negative infinity occasionally. That's because we're taking a normal value over value so close to 0 that our true value becomes so much larger than it should be. For instance, if I were to give you the ratio of 2/1, well, that's simply equal to 2. But what about 2/0.5? That's equal to 4. As our denominator becomes smaller and smaller, the ratio between our two values becomes so large. And that is why this value over here is actually equal to infinity. And so that's essentially the true value from -1 to 1 of 1/x² dx. So yes, this integral does in fact diverge.